Welcome to this learning module on filters, performance, and analysis. This presentation, developed by Marty Wanyalista, explores the use of filters as a best management practice, examined through the BMPFast framework. While filters have historically been used to remove particulate matter, commonly known as sand filters, the focus here extends beyond that traditional application. The content in this module specifically addresses filters designed to remove nutrients, representing an important advancement in stormwater and water quality management. This presentation focuses on stormwater treatment technologies, with particular emphasis on filters designed to remove total nitrogen and total phosphorus from stormwater runoff. These filters are commonly referred to as biosorption activated media, or BAM, and they represent an important advancement in how we approach stormwater quality management. We'll begin by establishing some foundational definitions and explaining why nutrient removal matters in the first place. From there, we'll explore how BAM filters are deployed in various configurations, including when they're added to baffle boxes, used after wet detention systems, and applied alongside other treatment practices such as retention basins, vegetated filter strips, tree wells, rain gardens, and exfiltration systems. A key theme throughout this presentation is that BAM is rarely used in isolation. It's typically applied in series with other best management practices, which we commonly refer to as BMPs. Understanding how these systems work together is essential, and we'll walk through how to calculate the annual pollutant removal effectiveness of BAM when it's combined with these other treatment approaches. We'll close with an assessment of current performance, a look at future research and applications, and time for discussion. Detention with filtration is defined as the selective removal of pollutants from stormwater through the collection and temporary storage of that stormwater, followed by its gradual release downstream through an appropriately sized engineered media or filter system. This definition comes directly from the Applicant's Handbook, Volume 1. In practice, the focus here is specifically on the removal of nutrients, particularly total nitrogen and total phosphorus. Filters are typically deployed after settling has already occurred, meaning particulates have been removed first. This sequencing is important because it significantly extends the life expectancy of the filter media. The Applicant's Handbook Volume 1, Appendix O, along with the Water Management District Volume 2 and the Manuals of Practice, outline the typical applications for filtration systems. These include inlet filters, media filtration following baffle boxes, vegetated filter strips, retention basins, and sidebank filters used after wet ponds. Each of these serves a specific role in the treatment train, but the systems of greatest interest for our purposes are those designed and proven to effectively remove nutrients from stormwater runoff. Biosorption activated media, or BAM, is a stormwater treatment approach that works through two primary mechanisms. The first is adsorption, where pollutants attach and bind onto solid surfaces within the media. The second is the physical entrapment of particulate matter as water moves through the material. What makes these media specifically biosorption activated is that they must maintain the right environmental conditions to drive pollutant removal. A key example is the need for low-dissolved oxygen levels, which creates the anaerobic conditions necessary to remove nitrates through biological processes. It's that combination of the right media and the right conditions that earns the BAM designation. These media are carefully engineered and selected to maximize the removal of target pollutants, and they are evaluated through actual field testing to confirm they perform as intended. The media formulations typically involve combinations of materials such as sand, clay, and carbon sources. Those carbon sources can include compost, sawdust, cardboard, paper, and various agricultural residues, among others. Manufactured media products are also evaluated as part of this work. The goal in developing these mixes is to find the combinations that most effectively capture and retain the pollutants of concern in real stormwater conditions. When selecting a biosorption activated media for removing nitrogen and phosphorus, there are several important factors to keep in mind. First and foremost, you want to understand the sorption properties of the material, meaning how well it adsorbs or absorbs these nutrients from the water. This directly determines how effective the media will be in your application. Life expectancy is another critical consideration. You want a media that will continue performing its removal function over a long period of time, making it a worthwhile investment. Closely related to this is surface area, since a high surface area allows for greater contact between the water and the media, which improves overall treatment efficiency. It is also important to ensure that the effluent leaving the system has no biological toxic effects, meaning the media itself should not introduce harmful substances into the treated water. From an operational standpoint, ease of filtration matters as well, since the media needs to work within your filtration system without causing complications. Maintenance requirements should be low, and ideally the media should either be reasonably non-degradable or capable of being rejuvenated and reused, which helps manage long-term costs. Speaking of costs, that is another key factor to weigh, along with the availability of the product in your region. Fortunately, there are many BAM products currently on the market, giving you options to compare and evaluate based on all of these criteria before making a selection. When it comes to biofiltration adsorption media, or BAM, there is actually quite a wide range of materials that can be purchased and used. Some of these are organic materials like peat, sawdust from untreated wood, paper and newspaper, wood fiber and chips, compost and coconut core. Others are mineral or inorganic in nature, such as expanded clay, natural sandy, loamy, or clayey soils, iron filings, zeolite limestone, and crushed shells. There are also some less conventional options like tire crumb and chips, water treatment sludge, and activated carbon. It is important to understand that this is only a partial listing of what goes into various BAM products on the market. The specific combination of materials used in any given mix is what ultimately determines two critical factors: how effectively it removes pollutants, and how long it will remain functional before needing replacement. Because of this, the exact formulation matters a great deal. One non-negotiable requirement for any media mix is that it must be tested for toxicity before use, to ensure it does not introduce harmful substances into the environment. And as you might expect, with such a diverse range of raw materials, the cost of BAM products can vary widely depending on what materials are included and how readily available those materials are in a given region. When looking at inexpensive, best available media products, there are several important characteristics to understand. Because these media are mineral in composition, they experience minimal degradation over time, giving them an expected service life of at least 30 years. That long lifespan is one of the key advantages of going with a mineral-based approach. These products are typically made from natural and recycled materials, which keeps costs down while still delivering effective treatment. Common components include recycled tire rubber, iron filings, sand, clay, and expanded clay. If there is ever a need to introduce organic components into the media, that is usually handled by incorporating a wood-based material. One of the most critical characteristics to evaluate when selecting an inexpensive BAM product is the filtration rate, because it needs to match the existing infiltration conditions of the site. For retention ponds, infiltration rates typically fall in the range of 1 to 10 inches per hour, while man-made filtration systems generally operate between 0.1 and 1 gallon per minute per square foot, which translates to roughly 96 inches per hour. The treatment or filtration rate is a major determining factor in which product you select, largely because it directly influences the overall cost of the system. Two examples of inexpensive BAM products designed with these characteristics in mind are ECT3 media and CTS media. Interest in beneficial aquifer management, or BAM, has grown significantly over the decades, and understanding why requires a bit of historical context. This technology has actually been available since 1977, making it far from a new concept. In fact, collaborative research with the Florida Department of Environmental Protection and the water management districts stretches back even further, to 1974, when the first studies were conducted on retention performance using select media. The push for greater adoption of BAM comes largely from the limitations of existing stormwater management approaches. Wet ponds, which have long been a standard best management practice, simply are not achieving the high removal performance rates that regulators and resource managers need, which can range from 80 to 95%. When conventional approaches fall short, engineers and environmental managers need alternatives that can actually meet those standards. Interest really surged around the year 2000, driven by increasingly stringent nutrient regulations. There is also growing concern about protecting sensitive ecosystems like springs and estuaries, as well as the need to increase and protect aquifer water supplies. BAM has been used in a limited research capacity for nutrient removal since the early 1970s, but as the demand for higher removal rates intensified and the shortcomings of existing practices became more apparent, BAM has earned considerably broader acceptance as a practical, effective tool in the water quality management toolbox. Upflow filters are a type of stormwater treatment system typically installed after wet detention ponds, and they're especially useful in situations where space is limited. What you're looking at here is an actual installation on the property of a retail store, which is a great example of how these systems can be incorporated into commercial development sites. In fact, this installation was considered a significant improvement over the old muddy pond that previously occupied that space. These photos, courtesy of Ferguson Waterworks, give us a real-world look at how an upflow filter is designed and constructed in the field. When designing a nutrient removal filtration system, the surface area of the filter is calculated using a specific formula that ties together the effective impervious area, the treatment depth, and a constant of 18.85. The effective impervious area, or EIA, is determined based on the treatment depth you're working with, and that relationship is important to understand before applying the formula. This approach is considered a conservative design method, meaning it builds in a margin of safety, and it has been accepted by most regulatory agencies. The specific guidance comes from a Florida Department of Transportation technical memorandum from June 2017, authored by Wanyalista and George, focused on the design of nutrient removal filtration systems, also referred to as NRFS. FDOT also has a technical specification available, and notably, no on-site mixing or media certification is required under that spec. The standard design uses a filter media depth of 24 inches with ECT3 media, and the entire calculation assumes a filtration rate of 1 gallon per minute per square foot of filter media. That assumed rate of 1 gallon per minute per square foot is actually embedded in the derivation of that 18.85 constant in the formula, and we'll walk through how that number is derived in the next slides. To summarize what you need to run this calculation: the treatment depth, the EIA, and the media type. The design also incorporates a factor of safety of 2, which contributes to its conservative and widely accepted nature. To understand how a wet pond handles runoff, we need to look at how the volume moves through the system over time. In this example, we have 1 inch of runoff generated from 24 acres of effective impervious area. The original site was 100 acres with a runoff coefficient of 0.24, which gives us that 24-acre EIA figure. The total volume works out to 87,264 cubic feet, and when we convert that through the unit math, multiplying by 12 to convert feet to inches, then dividing by the 24 acres and the 43,560 square feet per acre, we confirm that this equals exactly 1 inch of runoff depth. That unit check is a good way to verify the calculation is set up correctly. Now, the key design principle here is how that volume is distributed over the 3-day treatment period. Half of the total volume is assumed to be treated on the first day, and the remaining half is spread across the following 2 days. This split is a standard requirement for most wet pond designs. The system needs to demonstrate it can handle that first-day peak demand while continuing to process the remaining volume at a controlled rate afterward. The design maximum filtration rate is determined based on this distribution, ensuring the pond can meet that first-day treatment obligation without being overwhelmed. The surface area formula for a stormwater filter is derived through a mass balance approach, equating the volume of water filtered in one treatment day to the treatment volume that needs to be processed. Starting with the volume filtered, we use a treatment rate of 1 gallon per minute per square foot, which converts to 96 inches per hour. Because the volume under the storm event curve is assumed to be triangular in shape, we take half the total flow over the course of a day. That gives us the volume filtered expressed in cubic feet as 1/2 times the filter rate times the filter area times the unit conversion of 0.002288 cubic feet per second per gallon per minute times 86,400 seconds per day. On the other side of the equation, the treatment volume in 1 day is based on the effective impervious area, or EIA, and the treatment depth. That calculation is 1/2 times the EIA in acres times the treatment depth in inches, converted to cubic feet using 43,560 square feet per acre, and dividing by 12 to convert inches to feet. When we set these two expressions equal to each other through a mass balance and simplify, the result is a clean design equation. Filter area in square feet equals the EIA in acres times the treatment depth in inches times 18.85, divided by the filter rate in gallons per minute per square foot. An important practical note here is that the manufacturer's stated treatment rate is divided by 2 as a built-in factor of safety. The EIA itself is calculated as the runoff coefficient, or ROC, multiplied by the total contributing area, and this value is readily available from design software such as BMPFast. Many designers rely on a rapid reference table to quickly determine filter area based on a flow rate of 1 gallon per minute per square foot. Walking through the example calculations helps clarify how each column in that table is derived. For column 3, the maximum flow in cubic feet per second is found by taking 1 gallon per minute per square foot, multiplying by the conversion factor of 0.002228 cubic feet per second per gallon per minute, and then multiplying by the filter area of 14 square feet, which gives 0.0312 cubic feet per second. Column 4 calculates the volume released in the first day. You take that maximum flow of 0.0312 cubic feet per second, multiply by 86,400 seconds in a day, and then divide by 2 to account for the fact that only half the stored volume is released in that first day, arriving at 1,347 cubic feet. Column 5 reflects that the remaining half is also released, giving another 1,347 cubic feet, with the more precise extended value being 1,347.49 cubic feet. Column 6 then presents the sum of all water released over the 3-day period, and it is worth noting that some rounding of values occurs across the columns. Understanding these step-by-step calculations gives designers confidence in reading and applying the rapid reference table correctly for any filter sizing situation. This schematic comes from the St. Johns River Water Management District Manual of Practice, which represents the latest accepted guidance for stormwater design in that region. It illustrates one standard configuration for a side bank filter application, showing how the system is laid out and how the components work together. It is worth noting that this is not the only acceptable design approach. Review agencies will consider other side bank filter schematics as well, as long as they meet the applicable design standards. For nutrients and bacteria treatment using a side bank filter, the surface area calculation follows a conservative design approach that is accepted by most regulatory agencies. The formula used is filter area in square feet equals the effective impervious area in acres, multiplied by the treatment depth in inches, multiplied by the conversion factor 362.369. It's important to note that the effective impervious area is determined based on the treatment depth. The media used in this configuration is a sand-based CTS media, which is at least 19 times larger than ECT3 media. The filter media depth is set at 24 inches, and the design assumes a filtration rate of 0.052 gallons per minute per square foot. This lower treatment rate is actually a key design feature because it results in higher pollutant removal effectiveness compared to faster flow-through systems. To calculate annual effectiveness, you need 3 pieces of information: the treatment depth, the effective impervious area, and the media type. The BMPTRAINS tool contains media information organized by treatment depth and media type, and you can access this information directly from any BMP that uses media. Compared to an upflow filter configuration, the side bank filter offers lower structural costs, though it does come with lower treatment rates. So depending on site constraints and budget considerations, this trade-off between cost and performance is an important factor in selecting the right filter design. These are some typical media mixes that have been validated through field measurements to confirm their pollutant removal claims. Each mix listed here has an associated treatment rate that already incorporates a safety factor of 2. So there is a built-in margin of reliability in the design values. The depth of media shown represents the minimum required depth. You can always use greater depths, and doing so will extend the life expectancy of the media installation. For the ECT and ECT3 media types, removal performance is actually a function of the influent concentration, and specifically the ratio of particulate concentration to total concentration coming into the system. That relationship is important to keep in mind when evaluating performance expectations for those media. If none of the standard mixes fit your application, BMPFast does allow you to define your own custom media using the user-defined input option. However, any user-defined mix requires that field verification be completed before those removal claims can be considered valid. The footnotes referenced on this slide are listed in full on the following slide. All notes and guidance in this section are relative to current practice as of 2025, so the information reflects the most up-to-date standards and approaches in the field. The data shown here summarizes field performance results for CTS-24 and CTS-12 media systems, comparing measured nutrient removal against the credit values used in Florida's Environmental Resource Permit Program. For CTS-24, total nitrogen removal ranged from 73% at the Southwest 85th Street site, where influent TN was 2.71 milligrams per liter, up to 95% at DeLand when influent nitrate concentrations were relatively low at 0.303 milligrams per liter. At the Highway 26 site, which was treating groundwater with TN concentrations up to 5.7 milligrams per liter, removal reached 89%. The ERP program currently credits CTS-24 with 75% TN removal and 95% TP removal, and the field data generally supports or exceeds those values. For CTS-12, performance was somewhat lower, as would be expected from a less intensive treatment configuration. The horticultural technology pond in Marion County achieved 72% TN and 92% TP removal. The column and vertical flow systems showed TN removal of 69% and TP removal of 96%, while the vegetated filter strip bed achieved 80% TN and 84% TP removal. The ERP credit for CTS-12 is 60% TN and 90% TP, and again the measured data tends to align with or surpass those benchmarks. A few important contextual notes. The influent concentrations across these sites were generally representative of typical stormwater from roadways, with the exception of the Highway 26 groundwater treatment scenario. The DeLand site was primarily treating nitrate with limited particulates, making it behave somewhat more like detained water, and its TP concentrations were notably elevated at an average of 3.76 milligrams per liter. Each of these removal percentages was calculated from more than 10 field samples per site, giving the results statistical credibility for regulatory use. Here is a practical example of filter effectiveness analysis using a side bank filter with bold and gold 24-inch media. The results shown here were verified using a spreadsheet and cross-checked against BMPFast, with both methods producing identical outcomes, which gives us confidence in the numbers. The filter achieves between 75 and 95% pollutant removal for water that actually passes through the filter media. However, it is critical to understand an important distinction here. Not all of the annual runoff volume gets treated by the filter. Only the runoff up to the design treatment depth will flow through the media. Water from larger storm events beyond that design threshold will bypass the filtration process. When we account for this, the actual capture volume for the filter comes out to 78.58%, of the total annual runoff. This means that while the filter itself is highly effective at removing pollutants from the water it treats, the overall annual performance reflects that portion of runoff that falls within the design treatment capacity. Understanding this difference between filter efficiency and annual capture volume is essential when evaluating the real-world performance of any stormwater treatment system. Service life tells us how long a treatment media will last before it needs to be replaced, and it's calculated by dividing the total mass removal capacity of the media by the mass of pollutant removed each year. The removal capacity itself is determined by multiplying the removal rate, expressed in milligrams of pollutant per gram of media, by the total weight of media in the system in grams. So if you know how effective your media is on a per gram basis, and you know how much media you have, you can calculate its total capacity to remove pollutant over its lifetime. The mass removed per year is calculated by taking the annual runoff volume in acre-feet per year, multiplying by the pollutant concentration in milligrams per liter, then accounting for the fraction of runoff that actually gets treated, and finally applying the efficiency of the media itself. The example here works through this calculation using a unit basis of 1 acre of effective impervious area with an annual runoff depth of 48 inches, which gives us 4 acre-feet of runoff per year. This unit area approach makes it straightforward to scale results to different project sizes. It's important to keep track of unit conversions throughout both equations, since you're working across acre-feet, liters, milligrams, and grams, and those conversions need to be handled carefully to get a meaningful result. Also note that the treatment depth used in this example is 1 inch. Continuing with service life calculations, the fundamental equation here is straightforward. Total weight of the media multiplied by the removal rate gives you the service life of that media. When we apply this to a 1 acre effective impervious area with 2 different media types, the calculations play out in a specific way. The CTS media is typically designed to last well over 15 years, making it a long-term, low-maintenance component of the system. The ECT3 media, on the other hand, has a service life that ties closely to how frequently you would normally clean a baffle box, and anything over 2 years is generally considered acceptable performance. An important action item coming out of this is that these equations need to be built directly into the drainage design guide, along with clear access to the calculation methods, so designers have everything they need in one place to properly size and plan for media replacement over time. Retention basins represent another important application of BAM as a best management practice. These systems typically use around 24 inches of BAM material, and service life calculations are performed by evaluating the known capacity against the anticipated loading. The same equations we worked through in previous examples apply directly here. So if you followed along with those calculations, you already have the tools to analyze retention basin performance. What makes this particularly noteworthy is the scale at which this technology has been deployed. Based on data from an Excel spreadsheet tracking statewide installations, the number of retention BMPs using BAM exceeded 500 across the state as of 2020. That widespread adoption reflects the confidence practitioners and regulators have placed in this approach as a reliable and scalable stormwater management solution. This example walks through a retention analysis to demonstrate the level of groundwater protection that a biosorption activated media system can provide. In this scenario, the capture effectiveness of the retention basin is approximately 80%, meaning that 80% of the total average annual runoff is being infiltrated through the BAM layer rather than bypassing treatment entirely. The remaining 20% is not captured, but the majority of stormwater is being directed through the media for treatment. Of the runoff that does infiltrate through the BAM at the bottom of the retention basin, the media removes roughly 75% of total phosphorus and about 60% of total nitrogen before those pollutants have any opportunity to reach the groundwater below. This represents a significant reduction in pollutant loading to the subsurface environment. It is worth noting that this analysis comes from an earlier application of BAM dating back to 2015, where these removal rates were established as part of a permitted stormwater management approach. Those same results were later validated using the BMPFast modeling tool, and the outputs were consistent, which gives additional confidence in the reliability of these performance numbers for planning and regulatory purposes. Now let's turn our attention to permeable pavement systems, and once again we'll be looking at how bituminous aggregate mix, or BAM, has played a role in this application throughout its history. This analysis focuses on permeable pavement and its role in protecting groundwater. What you're looking at here is a historical reference from a 2018 ERP permit application, where an earlier version of BMPFast was used to evaluate pervious pave performance. The key parameters being examined are the area of pervious pavement measured in acres, along with the retention capacity, which in this case falls just under 1 inch at 0.874 inches. This kind of analysis was instrumental in demonstrating how permeable pavement systems contribute to groundwater protection within the permitting process. Here's a real-world example that demonstrates just how durable and effective these systems can be. Back in the 1980s, the bioretention area method was applied in the design of an exfiltration trench system as part of a permit application. What makes this particularly remarkable is that this system is still fully operational today in 2025, meaning it has been functioning as intended for over 4 decades. That kind of longevity speaks volumes about the soundness of the engineering principles behind these designs. The credits shown here were determined based on the use of exfiltration in an environmental review process. This methodology carries forward and continues to be applied within BMPFast. Media filters, and BAM filters in particular, give us another powerful tool for removing nutrients and other pollutants from stormwater. They work to improve both the quality and quantity of water that eventually makes its way into our surface waters and groundwater systems. These filters are especially useful when we need to address higher concentrations of nitrogen and phosphorus. One of the key considerations in working with media filters is service life. Service life becomes relevant when the removal capacity of a given media is limited by its chemical and physical characteristics or by the volume of water flowing through it over time. For orthophosphorus removal specifically, service life is directly tied to how much water has passed through the media and how much capacity that media has left to continue doing its job. When it comes to actually designing these systems, we rely on established design equations to properly size the filter for the application. Those equations are built directly into the BMPFast software, which streamlines the process of calculating both pollutant removal performance and expected service life. That brings us to the end of this presentation. Thank you for watching. That brings us to the end of this module on filters, performance and analysis, presented by Marty Wanielista as part of the BMPFast learning series. You are encouraged to explore any of the other available learning modules to strengthen your understanding, and when you feel ready, you can apply to take the test. For details on the certificate of completion, be sure to visit the module called Self-Test. Thank you for watching.